varying, and it varies with a bunch of factors. And that was just for your information. It's not something that I would quiz you or bring it into the exam, but you are finishing your electronic courses, and if you go somewhere else and talk about beta, and somebody says that beta changes with temperature or whatever, then you are not surprised. But because a lot of parts of this course that we talk about suits integrated circuits better than discrete level circuits, we mentioned what are the differences and talked a bit about the process technologies. These are not anything that you need to worry about on the exam. It actually starts from here. What you need to know starts from here, that we are talking about amplifiers that come one after the other one. And inside an op-amp, especially, we have a few stages of amplification. One of those, the middle section, usually is a single transistor amplifier. That's what we covered in introductory electronics. The first stage is the differential pair amplifier. That's what we covered in this course up to this point. And the last one is basically a current amplifier or a voltage follower that we have talked about it kind of in the introductory electronics. But in this course, we also are going to talk about it in terms of the power amplifier, because at the output stage where the voltage gain is high and we need to have high current capabilities, voltage times current both being high give us a power amplifier. So in that shape, we will have a look at that stage as well. So we started by introducing the normal or basic differential pair amplifier, and the condition that we had for ideal situation, that is all the components from the two sides of this circuit match each other, and both transistors are acting in active mode, or operating in the active mode. And then we showed a number of ways that we can use them, and some of them in large signal regime is not what we focus on in this course. So if we have a large input signal applied to the two inputs of the amplifier, then this is not an amplifier, it's going to be actually a logic circuit. And in that circuit, the bias current would completely be going through one versus the other branch. So one branch takes all the current and the other one is off and does not pass any current. So depending on what large signal we are applying, if it is positive or negative, one of the two transistors is going to be off, the other one is going to be on. What's the criteria for being large? We will talk about that when we get to the small signal operation, and we find that limit. But we also needed to know about common mode operation or mode of amplification for the differential pair amplifier. So these two were the most important, the differential and the common mode. However, in order to bring down our analysis to the small signal, we started from the large signal analysis. Okay, so we basically mentioned that also that when we have a common mode input signal, which could be a noise signal, when signal arrives at the two inputs at the same time, then the output, the differential output, is going to be zero. And that was the virtue of differential pair amplifiers, because differential input gets amplified, but common mode input is going to be eliminated. So noise is kind of eliminated, at least ideally. Okay? But for the large signals, as we mentioned, one branch is conducting the whole current and the other one is totally off. And we need to be able to analyze these in DC, but they're not amplifying, and those are not amplified. So we spent some time in analyzing the differential mode amplifier, and that's when we apply a signal between the two inputs differentially, and we're looking at the two outputs differentially. For that, to apply the differential input, we introduced balanced input, which had both differential input and the common mode. And then we went to large signal, and it started from large signal analysis. We applied a large signal to the input and looked at the collector currents, therefore the collector voltages, and we realized that in one transistor where we are conducting the whole current in large signal, the other one we don't see any current conduction, right? Whether this input is too large negative or too large positive, one of them is off, the other one is conducting. But it was at the middle of this curve that we realized some linear operation. That linear operation belongs to a small range of input signals. And that's why we call it small signal operation of the inputs. And we started by writing the equations that we know in large signal, which is going to be also valid for small signal, right? But we found the emitter current, and from there we found the collector current, and from there we came to simplify this collector current, which came from the large signal analysis, such that we get simpler relationship. And that's when we realized that we better be at the input much less than 2 VT. 2 VT is 2 times 25 millivolts, right? And then we could linearize the circuit, and the exponential terms that we had in expressing the IC. And using that, we came to the conclusion that there is a GM, which is alpha I half over VT. And this was something that we already knew, because alpha I half is IC, VT is VT, and we knew that from before that that's GM. But here we kind of reassured ourselves that this is the case. Then we came to look at the transistor in small signal operation, and when we applied small differential input, we realized that we have a amplified version of that, a small input signal. We found a gain for that in differential mode, and the differential voltage gain for the differential pair amplifier turned out to be the same thing that we had before, GMRC, or RC over little RE, which was an introduction to the Hawaiian dance for us last time. So that Hawaiian dance still continues to be valid in even differential pair amplifiers. But what was this good for? That we used 2 transistors, is the ability to eliminate the noise, an unwanted signal. We chose another approach, and in that approach we also showed that the RC over RE that we had, if we had external emitter resistances, all we had to do, we needed to place that external resistance next to the little RE in the denominator. Therefore, the Hawaiian dance still applies. And for the input resistance, we used the resistance reflection rule. Okay, and we found how much that is. And it's just a reflection of the resistances in the emitter to the bases. Then we looked at the differential pair amplifier in a different way. We looked at it as a pair of half circuits. Okay, so we could actually split the circuit in two halves. And that's when it became actually comparable to common emitter that we used to have before. So, and in fact, the same GMRC that we had and we just found for the differential pair amplifier was what applied to the common emitter, single transistor amplifier in common emitter configuration. Then we looked at the common mode situation for this amplifier. In that case, this emitter node was no longer at zero potential in AC domain, and therefore we had to take into account the REE, which is the internal resistance of the current source. Now, we found the voltage gain in this case, which is in the common mode situation, and it was ideally zero. So we defined a quality factor or measurement, a way to measure the quality of the amplifier, and it was called common mode rejection ratio, which was the ratio of the differential gain over the common mode voltage gain. So up to this point, that common mode voltage gain was zero. This common mode rejection ratio was infinite, ideally. But and then we found the input resistance for the common mode, and then we started looking at real cases. Nothing is ideal. So what happens if the resistances don't match? And we realized that there is a small but non-zero common mode voltage gain. So that contributed to a non-infinite common mode rejection ratio, which was dependent on the REE, the internal resistance of the biasing current source, the GM of the transistors, and the delta RC, or the percentage error of producing two same RC. But soon we realized that it is just the REE that we have a better chance to use in improving the common mode rejection ratio. And that was when we looked for current sources, better current sources, for a while. So then next what? Oh, 3, 4, sorry, 5. So this is repeated. I go to the 5th lecture, which is this one. Then we continued our exploration in the real situation for this differential pair amplifier by looking at this situation in a little different way. We said, okay, if there is mismatch between the two sides, when we place the two inputs to ground, and we should get zero output, we are not going to get zero output. So we end up with a non-zero output, which we can translate it back into the input as a voltage source, which we called it offset. So offset input voltage source, which was due to non-idealities, mismatches between the two sides of this structure. So, for a number of cases, like for the resistors we found, what's that offset voltage? It was VT delta RC over RC. For other factors involved, like the area of the emitter, if between the two transistors the emitter areas don't match. And then we got another similar relationship. And we basically realized that if we want to add up all these input offsets due to the mismatches between the two factors in the two branches of the circuit, we have to add them up like a vector, because they are independent processes that when we want to add them up, we should add them up statistically and vector. This is how we add all the results of all the offsets at the input and come up with a lumped amount of offset voltage at the input, which goes through the differential gain and give us a non-zero output. Also, we defined offset current, which was due to the mismatch between the base current, which could be a result of a mismatch in the betas, and we came up with a relationship for the offset current and the percentage error of the betas. So all these were revealing the non-linear situation that we could see the differential pair amplifier operating in. And then we had an example which pretty much covered very good the topics that we covered up to this point. I hope that you understood all these very well. If not, go over them. If you still have problems, come see me, office hours I have, or in any way that you can get the questions answered. This was another approach of that, which makes our job easy. We're just pushing the resistance in the base into the emitter. So I let you review that as well later, which give us the same result. This was the conclusion of this page, was that in both ways that we did this problem, we come up with the same response as expected. Then we started talking about current sources. And the current sources, we started with the simple current mirror current source, and which is based on a diode connected transistor. And we wrote a KVL in this loop, came up with the reference current, which ideally is going to be the same as this I on the other side, which gets connected to the emitters of a differential pair amplifier. And then we mentioned that the diode connected transistor in DC acts like a diode which can pass emitter current from its anode to the cathode. This is how the current source fits under the differential pair amplifier to bias it. And we realized that the REE that we were hoping to be relatively high, in this circuit is as high as the little RO. Okay. But we were looking for better output resistances of the current source so we could improve the common mode rejection ratio. Meanwhile, we also showed, it's just showing that, we could have a similar current source using MOS transistors. There will not be any MOS question in the midterm, okay? But then we focused on the simple current source, and we looked in the details of current that goes through all these components. And we realized that this I is not exactly IREF if we consider the currents that go into the bases, which means due to the beta that we have and is not infinite. So far, ideally, we said beta is infinite, so these currents were zero, and therefore IREF would end up equal to IO. But if we consider the betas, we realize a different story, in which there is an error when we relate IO to IREF. But that wasn't the only thing. Also, if we had emitter area mismatches, that could also contribute to the difference between the two currents. And that wasn't the end of it. When we had this collector potential connected to a different potential than what we have in Q1. In Q1 is the base emitter. So the collector potential is the same as the base emitter potential. But this collector could be connected anywhere because that goes to the emitters of the differential pair amplifier, and it could be different than the one on Q1. So we realized that we could get another factor which could make the IO more different than IREF. So this was the whole, the big picture that we had for the relationship between IO and IREF. It is a good equation to put on your formula sheet that we will talk about, the formula sheet. But still, the output resistance here is the little RO of this Q2. And we were looking for better than that. Meanwhile, we talked about how we can turn around the direction of the current in order to provide a bias current for PNP transistors. Okay, when we have differential pair amplifiers made by PNP. And also we learned about scaling factor, how we can scale the current, the reference current, to a number of reference currents. Then we tried to improve the situation for the simple current mirror current source by adding a transistor which was called beta helper. It was reducing the amount of current that we were stealing from IREF in order to provide into the bases of Q1 and Q2. So that helped a bit more in reducing the error. Then we continue with other types of current sources. We explored one that, it was basically the same simple current mirror current source, except in the emitters we had introduced a small resistance. And when we looked at it, especially in terms of the output resistance, we realized that it could give us a lot more larger resistance. And this was basically not only RO, but also a multiple of ROs added to that. So this is also another good equation if you want to write it in your formula sheet. And then we looked at other types, like Whitlock current source. And when we studied this, we realized that it is not that easy to find the I out, the output current of this by hand, and we had to use trial and error. But what we realized is that this was good for low amount of current, and the output resistance is relatively big. So at least it was good for introducing larger REE for us. And then we went to Wilson current source, which was also having a reduced error plus a relatively large output resistance. And when we looked at another one as Cascode, BJT current mirror, we realized that it does have an error that is not much better than the simple current mirror current source. I didn't give you the R out for this. I wanted, and I still do want you to go search for it. It's not going to be on the exam, but I'm hoping that some are interested in exploring that resistance and finding the output resistance for that circuit. And we put everything in the shape of this table, which is very informative about all these kinds of current sources that we covered. And finally, we talked about not so much important type of current source, which is the peaking current source, which the output peaks for some values, specific values of input current. Then we came to talk about other types of differential pair amplifiers. And before we do that, we had to cover Miller's theorem. Miller's theorem would justify the need for the cascode amplifiers, and it would simply say that we can convert a two-port network like this, where from the input to the output we have an impedance, to a two-port network that has an impedance on the input side and an impedance on the output side. Then we found a relationship between the two, which means between Z1 and Z2 and Z, and we used that in finding the gain of an amplifier that had a capacitor connected between its input and output. And we realized that it acts like a low-pass filter, which basically kills the input frequency spectrum. And then we introduced, we revealed that in transistor, unfortunately, we do have a capacitor, which sits exactly between the base and collector, which is usually input and output. And therefore, if that gets amplified here on the input side, then we are going to lose a lot of bandwidth. In order to avoid that, we came to cascode differential amplifier, where the gain of the input transistor was 1. So that magnification of that capacitance was the minimal in this situation. And still we could get the same gain of GMRC, or RC over RE from that. So this way, it was giving us an increase in the bandwidth, but at the same time we could have the gain that we used to have. After that, we explored another circuit that would give us the maximum differential voltage gain possible in all these circuits. And that was with the use of an active load, where instead of a resistor, which would demand a large voltage drop across it, if we increase it, we would introduce a big resistance, while the voltage drop doesn't have to be really that big. And therefore, it made it possible. And again, here, the active load is using a diode-connected transistor, which in AC we explored what that is equivalent to. And then we had to introduce Y parameters in order to find the gain of this amplifier. And for that, we needed to find a GM, just like a transistor, where GM would transfer the effect of the voltage on the input to a current on the output. We had to find a GM for this whole circuit. And we used the fact that GM is found by what we call the Y21 parameter. And we did the same thing in order to find the GM of this transistor. But we realized that that GM is the same as the GM of a small transistor. And it helps us in finding the gain, a relatively large voltage gain in differential situation. Then we found the common mode voltage gain for the same structure, which is the active load. And we formed our common mode rejection ratio. We realized that, again, it is dependent on the REE as well as beta and GM, which we have less control over changing them. So once again, in this circuit event, REE plays an important role in improving the common mode rejection ratio. And finally, oh, by the way, these from the Miller theorem. From Miller theorem to the end of this lecture, from the Miller theorem to the end of the active load differential pair amplifiers, I won't be giving you any numerical problems, but you might get some conceptual questions, okay, that you have to describe or explain and things like that. But no numerical questions, okay. I hope that does reduce a bit of your load and your stress. If you had any, you shouldn't. Not a big deal, just a midterm. Anyway, then we continued with multi-stage amplifiers. First, we talked about a two-stage MOS amplifier. Again, there's not going to be any MOS question, but this is a good, I mean, you could replace these with BJT transistors, and it's still, you know, it's an interesting problem. So we looked at a two-stage MOS amplifier, which we can skip, and then we came to a nice four-stage BJT amplifier, and we started by DC analysis. We always need to start with DC analysis. Usually in multi-stage amplifiers, for DC, we assume beta is infinite, which means the transistors are in ideal situation. Now, we had to find a place that we had the most information, all the information we needed for the analysis, and that was this DC bias circuitry. We had all the information. We started by analyzing the current mirror current source, which would give us the current demanded from the emitters. It would split in two parts, would also go up here to the collector resistances, drop a voltage across them. And the same way, the current on the second differential pair amplifier would get a split between the two equally, and then drop a voltage on the resistance, which would determine the input voltage, DC input voltage, to the next stage, the third stage. We used that and analyzed it to find the emitter and collector current of this transistor Q7, the third stage, and then finally we found the currents and voltages of the last stage. And we did that with zero inputs because we were hoping that we get a zero output, and that should be the case normally. If the design is good, then you get a zero output. Then we continued with the analysis, AC analysis of each stage. So we went stage by stage and looked at the effect of the next stage on the previous stage by the resistance that we would see into the next stage. So that would also contribute to the load of the previous stage, and we would have to use it in finding the voltage gain for each stage. So we found the voltage gain in most of these cases. The Hawaiian dance worked and gave us the result. First stage, second stage and third stage, all of them were considering the effect of the next stage input resistance on the previous stage. And with exception to the last one, which is a current amplifier, or it's a voltage follower, whose gain is 1, close to 1. The others were giving us high amplification. We amplified them all together, and we came up with a relatively big number as the voltage gain. The voltage gain of this multi-stage amplifier. But also, as we had found the input resistance, the voltage gain, another important information or data that we usually need about amplifiers is the output resistance. So that's why we found output resistance here. We used resistance reflection rule. That comes handy in a lot of places. Make sure you do understand that. And we also looked at an alternative way that we used current and how it progresses through the circuit to the output. And that's how we came up with the voltage gain alternatively for the same circuit. But, I'm not going to ask you to do it in a specific way if you are, which usually everyone is, feeling easier doing it in the previous way or approach. So this was just for your information. You don't really have to follow this if you don't want to. If you feel easier doing this, fine. You can always use that. And then we went to the feedback, and feedback is not a part of the midterm, so I'm not going to go over that. But so from the beginning to the multi-stage amplifier is going to be on the midterm, with exception to numerical questions about Miller theorem, cascode differential pair amplifiers, and differential pair amplifiers with active loads. Okay? This was the technical aspects of our review. If you have any questions right after typing me, you can start asking, please. Go ahead. Type me, please. And Aiden has a question, please.
I was just going to go over, just because I didn't actually get to write it down in time. You gave, you were saying like 2 or 3 equations that we definitely needed to know, or would be good to write in a formula sheet.
Well, all the formulas you definitely need to know, but some of them are important, and some of them are really harder to remember. So definitely the one that gave you IO versus IREF, for example, is better to be on your formula sheet, so you don't have to memorize it. I can't recall where else. Somewhere else I said, there are other equations. Whatever equation that is, relatively bigger, is harder to fit in our mind. We can put it on the formula sheet.
Okay, and one other thing was, some people are asking specifically about the formula sheet and what is allowed to go on it.
Yeah, I was going to talk about it. Okay, this is a good time to talk about it. You can put just about anything on it. However, you are limited to 2 pages. 1 page, 2 sides. 1 sheet of paper, 2 sides of it. Okay, so I wouldn't fill it up with all of the material, or otherwise, it will really become confusing for you. But just put the things that you can't really remember. Okay, like the big formulas that I mentioned. You want to put the schematics? Go ahead, put the schematics. But it's not. Schematics are the things that you can remember. I mean, I'm not giving you any numerical question about the the cascode and active load. And the remaining is the basic kind of the differential pair amplifier. You want to put that there? Sure, go ahead. I mean, use your space wisely. That's what I want to get to, basically. So I don't mind you putting anything you want, but remember, I'm going to be looking at that formula sheet. It better be complete, which means it should reflect that you have reviewed from the very beginning to the very end. The beginning could start from the introductory to electronics. If you don't remember IC is beta IB, okay, go ahead and put it there. You can do that. But it's limited to only 2 sides of the formula sheet, and you will be uploading it at the end of the solution, your solutions to the midterm. We'll talk about that more. All right, so let me copy paste this and try. Okay, and now let's go. Any other technical questions about the technical aspects of the midterm?
People just have a few in the chat.
Oh, on the chat. Okay. Could you show the big formulas again? Oh boy. How about if I let you go look at any formulas which are big and put it? I mean, I'm not saying that you must put anything specifically on your formula sheet, but whatever you can't really remember, go ahead, put it there in your formula sheet. So let me see, before I lose the question, what is not going to be numerical questions? Miller theorem, cascode, and the last one is the differential pair with active load. How many questions? Okay, this is the thing, the exact duration and the number of questions, I really don't know until the very last moment. I keep changing, adding, deleting a question until I find the right structure for the exam. So, but it will be definitely fitting the time that is given to you. So it's between an hour to an hour and 15 minutes. And, it wouldn't make sense if I say 2 questions or 10 questions, because you can actually have 10 smaller questions in the same time versus 2 larger questions that fit the same time. So don't worry about that. I will give you a reasonable number of questions in the period that is given for the exam. This and active load, yeah, that's what is not going to be there. How many questions? So that's what you want a hint? It's less than 50 questions. Okay, that's my answer always. Okay, thank you. Are they only numerical or theory as well? Oh, I think I did answer that question. So there are going to be numerical and theoretical, or whatever you want to call it, theoretical or descriptive or conceptual questions. There could be. All right. So now let me go to the procedure. Let's have a look at what we need to know in terms of the steps when it comes to the exam. Okay. First of all, let me remind you, these are the review notes from the introductory electronics, and even though we didn't go over them, but the knowledge contained in these lectures is really important for us. As well as it is good to go over the tutorials. And, you know, I realized that the TA actually solved the problems of this week's assignment a week before. So she did that by mistake, but that's okay. Well, it's just 2% of the whole grade that you will get. And what else do we have here? And our lecture notes that we went over them, you know, so far. But what you're going to see is this, a module called midterm. The midterm questions is going to be here. The midterm submission is also going to be here. So you don't see the midterm questions yet because I haven't finished it. I haven't completed the question. But it will appear next to this somewhere here. There is also a quiz that I have mentioned in the announcement. It's going to be available from 1 a.m. tonight, after midnight, 1 a.m. until Friday night, midnight. And it is a bonus quiz. It's about the procedures that we need to do, and so that's hopefully helping you to better understand the process in the midterm. But let me go to the announcement and look at the latest announcement, where we lay out everything that we need to know, and you know, that's on top of what we had mentioned before. So let's go over that first, which is the first announcement, the previous announcement. In that, I emphasized that the exam is on Saturday, November 6th. It starts at 2 p.m. And I said I don't know the time. It could be between 60 minutes to 75 minutes, an hour, 15 minutes. The link to the midterm will be posted on Canvas. On that module, the midterm module, it's going to sit there. Okay, it becomes published at the right time for you. The exam format will be in the form of long answer questions. So it is pretty much like you were taking it in person on campus, but the questions appear in front of you. You can go back and forth between the questions. In fact, the question file, there is nothing that you need to do or enter in that file. It's just a text file, and of course it does have schematics as needed, but you just read it and write your answers in the on the papers that you have, the blank sheets of papers that you have in front of you, and then you upload it. But let's get to that. So the exam is long answer questions, which include both numerical and descriptive, or conceptual, or theoretical, as you called it, and the students have to show their work, all parts of the solutions to the problem, and the students will write their answers on blank sheets of paper and scan them before uploading the answers in the form of a PDF file, only PDF, please. And I believe somewhere else I say that it should be on paper, not on a tablet, okay? Or I don't want you to create it electronically. I want you to scan it and convert it to electronic file. So the exam is closed book, closed note, with no aid from nowhere, whether living or dead, like a machine. One formula sheet you can have, and that formula sheet has the normal size of the paper, both sides, but it must be handwritten. I hope that you realize the importance of that, because that is how you can learn better. When you summarize things, the least is that you've gone over it once, and therefore, when you write it, it kind of penetrates mind, whether we want it or not. Now, if we photocopy it, or even if we write it from someone else's, is not as effective as you do it yourself. So please do make sure that you do write it yourself. And as I said, I'm not limiting you on what to put on it, but just make sure it doesn't exceed 2 sides of the paper, of an 8.5 by 11 size paper. This sheet must be included in the uploaded PDF file as the last page or pages if it is two-sided, which should be two-sided if you do a complete study. Inclusion of the formula sheet in the correct manner would be worth up to 3 bonus marks. Basically, it's the formula sheet which is worth up to 3 bonus marks. For example, if I see a formula sheet with 2 equations on it, it's worthless, right? It shows that the student has not really done the review. So I want you to fill it up with whatever you need, but fill it up. Let's have both sides. Let it reflect your hard work or your effort. So that's what I will mark actually about the formula sheet. If it is complete and reflects that the student has really reviewed, it must be your own handwriting, otherwise it gets 0, and it must be at the end, not at the middle or not in front of the question, at the very end of the question. When the questions are done, then we have the formula sheet. So use of computer would be only permitted for viewing the question, and searching in the computer files or folders or anywhere online would not be allowed. So we're not using Respondus or the lockdown browser, but we are relying on you and trusting that you won't be using your computer for anything else other than viewing the question. The scope of the exam is already talked about. It will be to the end of the topic of multi-stage amplifiers, and we will do a complete review as we did. A simple calculator can be used for calculation. Please do not use cell phones as a calculator. In fact, your cell phone must be off and away from you. Okay? Only at the end of exam, when the time is up, you have 10 minutes to upload. And during that 10 minutes, you can turn on your cell phone in order to use the scanning app to scan the papers. Okay. The class list will be divided in 3. That's explained right up there. And stay tuned for more instructions. So here we come to this part, to this other announcement. And once again, I'm emphasizing that the exam is Saturday, November 6th, and it starts at 2 p.m. Now, what you need to do, you need to look at your last name and the first letter of your last name. If it sits between A to F, you come to this Google Meet. If it is between G to O, this one, P to Z, this one. And there is another Google Meet just for emergency situation. Okay, if something happens, God forbid you get sick or something, if something unexpected happens, you come here and talk to us. You let us know. But this is not for questions like should I take beta equal to 100 for this? If it's not given, either you don't need it or you can make an assumption. Okay, so go ahead and explicitly express your assumption if you feel that there is a lack of information in in providing you the problem. But so um, this link is for very important and emergency things. So I don't have to ask you for this, but you better have a quiet area to sit and focus on your exam. You must ensure that you have a reliable internet. Again, that's out of my hands and control. So it's your responsibility to provide alternative plan B, for your internet if you need to, like a hotspot or something. So we come on the Google Meet at 2, and from 2 to 2:05, I will just quickly go over the necessities, and I will review the procedure very quickly, and then at 2:05, the questions will be available for you. And you will be working on the exam after 2:05 by writing on a blank sheet. Blank, it doesn't mean that it has to be with no lines. It could be lines or completely blank. But if it has lines, make sure that you write darker than the lines so we can read your writing. And obviously, you need to make sure that your scanning is perfect so we do see your paper with a good quality. Using a tablet for writing the exam is not permitted. So once again, remember, just write on paper, please. You must have your camera on and your microphone on, but speakers down or off. Why we need to do that? Because the invigilators are going to need to hear you and everyone else, but you should not actually see. Shoot. I think I lost my internet. Guys, do you hear me?
Yeah, we can hear you, sir.
Okay. So I'm on the phone. That's why you have my audio, but you probably lost my video or is that right?
Yeah, with nothing's changed. It doesn't look like. It could be lag.
Oh,
but...
okay. Okay. So if you are seeing it, I can just read over it. That's good.
Okay, now it's gone.
Okay. So as I said, you need to have your microphone on, your camera on, but your speaker down, so that you don't hear others. Invigilators need to hear you, but you don't hear others. Now, let me try to use my alternative internet. Okay.
Yeah, I think I'm back, but let me get on my phone so that if it happens again, I don't lose my audio. But I have to go out and come back in. Just hang in there, please.
Okay, I think I'm back, and I see that Julius has questions, but you can't wait till we finish, right? If you can't, go ahead.
I can wait. I just wanted to put my hand up. It's okay. I'll wait until afterwards.
Okay, thank you. So let's finish this announcement, and then we will come to your question. So, oh, I have to share again. All right, just a moment. Okay, you can see my screen, hopefully, and great. So, we were here. Yeah, we went over the microphone, camera on, speaker off, to receive any possible messages. This is important because we might have a message to send to you. And for that, you need to have the chat area of your Google Meet visible underneath the Canvas window, which questions are there. Okay, so anything pops up on your chat, you can see. All right, you can dedicate a small portion of the right hand side of your screen to that. Plus, I'm sure that many of you have additional monitors. You can dedicate one monitor to that. But if not, at least a part of the side of your screen can be used for the chat to be viewed, just in case we need to talk to you guys. You must use only your formula sheet handwritten, and I think we mentioned all that. A module called midterm that I showed you will appear on the home page, and the questions are going to be there, as well as the link for submitting that was there. I have to complete that as well. By the way, whatever the time of the midterm is going to be, for SAS students, I will scale the submission link, because the exam link or the midterm, when it appears on Canvas, is just questions. Okay, so I'm going to set the time for the questions the same as for the non-SAS student. Okay, but the SAS students have more time to submit their work. So hopefully, by the time that non-SAS students finish it and the questions are not available anymore, you have written it down somewhere on your paper, and you're just continuing to work on the problems and solving them. But you will get more time for the submission of the paper. Aiden, you have a question? You can't wait?
In order to just save us from writing them down, basically, is there any way that we could just make it a downloadable PDF?
Downloadable PDF.
Yeah, because I feel a lot of the other classes that I have that go and do basically similar style to this, they'll make it just a download. I know, I know my computer aid midterm that I just had.
No, I just realized why. Because the questions are random, so it's coming from a pool of questions. Oh. I can't do that with a PDF. Yeah.
Okay.
Yeah.
But there will be backtracking. What? We can go back and forth to quickly write down.
Yes, you can. You can. Yeah. Yeah. All right. Then to submit the exam, you need to scan all the pages, including the formula sheet at the very end, as a single PDF file. So please make sure that you have everything on one file, not a file for each question. Okay, that would be disaster. You can't actually upload them all. You can only upload one file. Okay. And then use the link for submission to upload it. You will be given 10 minutes. 10 minutes is for everyone, but you know, this 10 minutes is added to the SAS student's time for uploading your file. So please make sure you have a good scanner app on your phone, while your phone must be off during the exam. At the end, you may turn it on for scanning. There will be a bonus quiz, as I mentioned, that, you know, is a maximum of 2 marks. And I hope that everyone gets the 2 marks, because that shows that you understood the procedure. And you have 48 hours to do that quiz, okay? Just about. Does that make it 48 hours? I think so. From 1 a.m. tonight, after midnight, to 1 a.m. of Saturday. Yeah, that would be 48 hours. Actually, not 1 a.m. on Saturday, 12 midnight on Friday. Okay. And also, please be advised that there is not a second lecture. So on Friday, we are not meeting. We're not having a lecture. You know, instead of your Saturday, that exam would have to be on your lecture time, and now you're spending your Saturday on that. I'm giving you that Friday night off so you can work more on your studies. And listen carefully, please. You will have the opportunity to come and ask your questions from me on Thursday office hours and on Friday office hours, okay? After 1 p.m. Friday, which is the end of my office hours, I'm not answering any question, not even through email, please, okay? So make sure you come with your questions the latest on Friday from 12 to 1. And hopefully then after that, you're just reviewing your studies and becoming more prepared for the midterm. One other thing that I have forgotten to mention in these announcements is washroom. You know, you won't have time to go to washroom because it is just 1 hour to 1 hour 15 minutes, right? Exam. So I recommend you use the washroom before you come to the exam so you don't have to take a break. You won't have the time for that. So in a way, there is no washroom break permitted. But, you know, even if it were permitted, you wouldn't have the time, or you would lose, you know, your time in answering. So the time is going to be tight for whatever number of questions you have there. And that's why you should try to use your time efficiently and not for a washroom, for example. Okay, let me see. I think I have gone over most everything. Now, if you have any questions, please let me know. Let me see if I can see anything. Okay, yeah, Aiden, go ahead.
I just want to be clarify something. You were saying that there was a 10-minute submission time, but it was included in the SAS students' time. What did you mean by that specifically? Does that mean that the SAS time will, the extra time allotted, will include?
There is 2 parts in the exam. One is answering the questions. The other one is scanning and submitting it, right? Scanning and submitting doesn't need a scaling time. It doesn't need any extra time or accommodation of anyone. So that 10 minutes is the same for all students. However, the answering part, SAS students' time will be scaled based on their accommodation.
Oh, okay.
So
the students will have their accommodated time. The questions themselves will close with the normal allotted time. So
yeah,
we've had them written down, and then then they'll have the time to submit, or the submission box basically will go to the extra time or the allotted time they're given, and then
plus
after
10 minutes. Yeah, after that, 10 minutes for submission.
Okay, there will still be so the timer that we can use basically to keep just so that we're not constantly watching the clock would be considered the time of the submission.
Yes,
Okay.
yes, but you know, the reason I'm doing this is that now I don't have to scale the midterm, the questions, because you know there's like 15 students in SAS program that I have to make changes twice. So it is like 30 changes, and I can make a mistake in that. Okay, but when the normal time finishes, the questions will not be available anymore, because that is a good indication for the majority of the class that now you need to go spend your 10 minutes or you won't be able to submit. Okay, so hopefully they get the signal, they go for submission, do the scanning, and submit through the link. Oh, let me show you how you can submit quickly, and you know, hopefully you spend less time in that. You see, if you click on midterm submission, there is, actually, if you preview it, then there is a choose a file that you click on it and your file in order to upload it by submitting the quiz. Okay, so it's like you're taking a quiz, but it is actually just the submission of the midterm through a file upload. Okay, so that's pretty much it. So do you see any questions on the chat that I missed? Let me see. I can see one. But SAS students go longer than the standard time, so they will have to worry about the questions disappearing. You know, I don't think you need the questions after an hour, right? So you go through the questions, you look at them, you write down whatever you want for question 1 on one page, for example, question 2 on another page, and so on. So after the end of the non-SAS students, the questions disappear. I'm not sure. Maybe I can do something that it won't disappear. But no, I want it to disappear so that the non-SAS students, which is the majority of the students, get the signal preparing for the submission. But then you guys, the SAS students, should manage their own time until the end of the submission time to make sure that they are submitting within the time that they have. Let me see if I can read others. I prefer to have another review session. Corey, go over, you do your own review, come to me during the office hours. Any question you have, I guarantee that you will get the answer. Okay? General question, but would this midterm be a good indicator of the types of questions we could see on our final exam, since that one is going to be in person. Yeah, because this is not like multiple choice or whatever that we used to have last term. The questions that you see, I mean, they are definitely different than final, but the trend is the same. Yeah, you can assume so. And can we have at least 2 attempts for submission? Yes, definitely. I'll give you 2 attempts just in case you miss it once. Make sure you don't get an error message. Okay, so if you get an error message, that's when you come to that emergency connection or Google Meet. Okay, and make sure it is in PDF. It won't be accepting anything yet. Okay, and great. Thank you all for your attention. And let me see, anything else this last second? I guess not. Just go ahead and type me for me, please. Thank you. So go get busy with your own review and writing the formula sheet, and don't miss Friday. That's the end. Friday, 1 p.m. After that, there is no opportunity to answer questions. Aiden, and then Julia.
Sorry, I think I'm going to just repeat myself just because I'm still a tiny bit confused on the submission thing for the SAS. Just in terms of, so I'll basically have that extra time potentially, and then it'll also include the 10 minutes that we would get to submit. Just because it's like normally you would have the questions disappearing to notify you for your 10 minutes. So those with the SAS time, the submission time will include the 10 minutes. So when we are signing off of the Google Meet, is that when we are allowed to then start taking pictures for our 10 minutes basically? Or do we have to keep on the Google Meet while we're taking pictures?
Yeah, let me see if I can actually clarify that by going to a file here. Let me see. I have to share my screen, but just before that, let me do this. Add a page here. And okay, here I can okay, let me share my new screen with you guys. Okay, so do you see the blank sheet of paper that I have, right? So let's say the exam period is this much for non-SAS students. And then they have a 10 minutes to submit. Now, for SAS, based on their accommodation time factor, they get the extra time for writing the exam, but they are going to get the same 10 minutes for submitting. Okay, so this is the part that you get the questions, and actually this is the time that everyone gets the question. Okay, and then this is just the time for submission. Now, for SAS, the same time for question, it's going to be the same, like that. Okay, from here on, you have to manage your own time because you have this much time extra, plus the same 10 minutes to submit. Okay, but because you're not seeing the questions anymore, and the period for majority of the students to see the questions is gone, and I'm using the same file for you guys. Then from here on, you manage your own time on solving your problems, and then your 10 minutes to go and submit. Okay. Does that clarify?
Yep. Definitely
Aiden?
clarify stuff. Thank you.
Okay. Thank you. Julius?
Yeah, hi
Julius,
there. I
hello.
was in tutorial 4 today, tutorial 7 today, and we kind of ran out of time while doing question 4, so I got like a very fuzzy understanding of it. And I was wondering if you're able to run through tutorial 7, question 4, so I can get professor's point of view on it.
Okay, let me see if I can quickly open that. And these are the type of questions. Now, I'm going to answer your question, but I mean, if others have similar questions, it's good to come to my office hours tomorrow or the day after. But let's go for this one.
Yeah, normally
So
I would bring it to an office hour, but it's a review day, so I figured.
That's okay, yeah. Our time is up, but that's okay. For this one question, I can actually, let me see, tutorial. Today's tutorial, right?
Today's tutorial, yeah.
Today's tutorial that she has uploaded. And okay, oh, I have to share it with you. Share again this window, which is this one. Okay, and did you say problem 4?
Problem 4, yes, please.
Is that this one?
No, that would be problem 1, I'm pretty sure.
Okay, problem 1, yeah.
Yeah.
So problem 3 says,
There we
problem
go.
4 is this one?
Yep.
Okay. Yeah, this is a lengthy one. So let me see if I can try to explain it as quick as possible. So this is, if you look at the circuit, it is symmetrical with respect to the middle of the image, right? So for the differential voltage gain, you can split it into halves, while the center of this little RE is ground, as well as the center of this RL is ground, because the potential across these resistances, this RE and the RL, are opposite to each other with the same magnitude. So somewhere at the middle, the potential has to be 0, right? So if you bring this, I don't know if she did it. Oh, she hasn't. Let me see. This is it. So she's not. She is not drawing it. Okay, she's not drawing it for different situation. This is just okay. I wish I had my own. Okay, let me see if I can write on anything.
If this would be too long, I can bring it to an office hour instead.
I would appreciate if you do that, because yes, it is going to be long.
Yeah.
And yeah.
Sorry, I thought it'd be a quick run through, but yeah.
Yeah, but this is a good question to focus on, because
Which
it does have
would
have everything. It does have everything in it. Okay, most everything. That's why I asked her to review that question again. So tomorrow, Thursday, what time is your office hours? You know?
Sorry, I actually don't know the office hour.
Okay, so let's go.
It's I believe it's from 4 to 5.
Oh yeah, I can do that.
4 to 5? Okay, thank you. 4 to 5. All right. So 4 to 5 is the office hours, and 12 to 1 on Friday.
Yep.
Okay, I hope to see a lot of you, and we try to go over this question definitely. And was that Julius asking?
Yeah, that'd be Julius.
Okay, yeah. So definitely I see you tomorrow or the day after.
Yeah, I'll probably see me tomorrow. I might be busy.
All right.
Yeah. All right, thank you.
Sure. Thank you very much, everyone, and see you, many of you, in office hours, others on Saturday then. Take care.